Hello, my name is Rob Reynolds, and welcome to College Algebra Section 2.2. In this lesson, we're going to look at graphs of equations, and um, a lot of the graphs will be linear, but some of the graphs will be quadratic. We're also going to be looking at cubic graphs, and we're going to be looking at some of their properties of symmetry as well. So you should have a couple of these graphs memorized. If I give you y is equal to the absolute value of x, then you should know that that's going to graph a v. If I give you the square root function, you should know the general shape of that. It starts at 0, 0 and goes over to 4 and up 2 because the square root of 4 equals 2. But this book is going to start out by saying, hey, if you don't know these shapes, the easiest way to find those shapes is just to plot points. So plug in for x and solve for y and make a quick little t-chart. And I'll show you how to do that on your graphing calculator. So here's just a complicated, but the reason why they do that is they have x and y ordered pairs for dates and prices, and they plot a bunch of points so you can see. It doesn't have to be linear, it doesn't have to be quadratic or cubic, but they're just plotting an x value and a y value to see any kind of a graph. So again, for this particular problem, you don't need to graph this function on a graph to find out if these points are actually on that function. Really, all you need to do is plug in for x and solve for y. So -3 times the x value plus the y value should equal 6, and we're going to plug that in. So for the x value, we're going to let x in this first scenario be 0. For the second value, for the y value, we're going to let the y value be 4, and we're going to check to see if that's true, and that's not true. The next statement says the same thing, -3 times its x value plus its y value. We're going to check to see, does that equal 6? And I don't think that it does. If I plug in a 2 and a 0 here, that is equal to -6. The last point, letting x be -1 and the y value be 3, I think might work. -3 times the x value plus 3. So this is 3 plus 3, and that does equal 6. So this was a no, no, and a yes, and I don't have to graph anything. If you did graph them, you can see if I would have changed this to a -2, that would have worked, but a 2, 0 does not work. Same thing here. We're going to plug in values of x and solve for y. And the first x that we're going to let this be is 0. So 2 times 0 plus 5 is 5. 2 times 1 is the next x value. 2 times 1 is 2, plus 5 is 7. So quickly making a t-chart. 5, 7, let's see, 10 plus 5. Oh no, I'm sorry. -10 plus 5 is -5. And if I plug in a 10, I get 20 plus 5, which is 25. And I can quickly see I'm not going to go by 1s. I might count by 5s if I were to graph this. Some of you know how to graph this a different way by starting at 5 and then doing my slope, rising 2 and running 1. And that's really not the goal. In this case, my goal is to plug in for x, solve for y, plot 4 points because they're giving you 4 x values. So they want you to plot 4 points and solve for y. This can also be done on your graphing calculator if you go to your y equals and type in 2x plus 5. And instead of hitting zoom 6 to look at the graph, let's go into our table setup, which is my second window. And it looks like I want to go, well, I'll go by increments of 1. This is the table change. So for each y, it's telling you the distance of each y value. But I want to start at x equals, well, we'll start at 0. And if I hit second graph, I get an instant t-chart. So I don't need to plug in for x and solve for y anymore. I can see all of the values. 0, 5 is here. We can see what happens at 1. We get the 7. If I scroll down to -5, we can see that we get a -5. And if I hit zoom 6 and actually do look at the graph, you can also find the values by hitting trace 10, enter, and the y value, whoops, and I'll hit zoom 6. I must have hit something funny here. Zoom 6 just resets my graph. Again, if I hit trace 10 and then enter, I should get a y value, there it is, of 25. And I could do the same thing with -5. So there's two ways to find a t-chart. You can go into your graph and do a quick table setup, or if you just trace the function and type in the x value, it'll individually give you the y value. Here's a quick graph. You can see what this function actually looks like. This next function is called a quadratic function. It graphs a parabola, which sometimes a play on word is parabola, because that's what it looks like, is a bowl shape. Some of you already know what this graph looks like again, but the author here wants you to actually plug in for values of x and solve for y. So be careful when you plug in a -4 and square it. If you don't put parentheses around the -4, you'll actually get a wrong answer. -4 squared is -16, but if you type in -4 with parentheses around it and square it, you'll actually get a +16. So be careful how you type that into your graphing calculators. So this function is going to start at 0, 0. Again, I'm renaming the x-axis. I'm counting by 5s again. And you can do that in your calculator as well. Your final solution should look like this. Finding the intercepts of a graph, we have some things called x-intercepts. In this case, I've got 3 x-intercepts, and in this particular scenario, I've only got 1 y-intercept. You can actually have more than 1 y-intercept, but then it's no longer a function because the vertical line test does not pass. This is actually called a double root. Remember, roots or x-intercepts or zeros, they're all names for the same thing. So some people call them zeros, some people call them x-intercepts. This is called a double x-intercept or a double zero, or I call it a double root. And it just means that my factor must be x plus 3 quantity squared, because when I set that factor equal to 0, I get -3, but I actually have a double root, so it's bouncing at that particular root. This is a single root, it passes. This is a single root, it passes. So if I give you an equation, we can actually find x-intercepts. Notice that this x-intercept, we're letting y be 0. The y value be 0, the y. So that's a neat little rule. To find an x-intercept, we're going to let y equal 0. And to find a y-intercept, likewise, we're going to let x equal 0. So that's what this slide's talking about right here. To find an x-intercept, let y be 0. To find a y-intercept, let x be 0. So following that rule, to find the x-intercept, if we let y be 0, I'll get 0 is equal to x squared minus 4. Either I can factor this or set it equal to 0. Either way, if you were to set this equal to 0 and get x squared equals 4, remember when you take the square root, we get 2 answers. So plus or minus 2, those are my x-intercepts. The y-intercept is found by letting x be 0, so this is a little bit easier. 0 squared minus 4 will be -4. So I can kind of quickly see, since I know the general form of an x squared function, I know it's a parabola, and I've got x-intercepts, and that's a quick sketch of the function. This is what it should look like. Testing for symmetry of a function. To find out if it has x-axis symmetry, that means it's going to reflect about the x-axis. Notice that this point, xy, comes down here to be x negative y. So the definition for x-axis symmetry is I'm replacing y with negative y. For the y-axis symmetry, it's kind of what we were looking at with the parabola. I'm replacing not y with negative y, but I'm replacing x with negative x. So they're opposite. So for x-axis symmetry, I'm replacing the y's. For y-axis symmetry, I'm replacing the x's. And for the origin, it's reflecting over the x and the y at the same time. So it's like this point goes here, and then it jumps down here. But basically, I'm replacing both x's and y's with their opposites. So a function like this would be an x cubed function, y equals x cubed. These are also called odd functions. They reflect about the origin. And notice that I'm making the signs opposite. So I'm going from positive to negative. I sometimes call this the 3-0 rule. For quadratics, or could be anything even, so this is even, an even function opposed to an odd function. It has symmetry about the y-axis. If I flip this function over this green line, the left side of the function should fall onto the right side. And then this one's called x-axis symmetry. This is what's happening. I'm replacing the y with a negative y, so I know it has symmetry about the x-axis, and I'm flipping it over the x-axis. By the way, the equation for this is not y equals x squared, but this is actually x equals y squared, the equation of this. In order to graph this, you would have to take the square root of both sides and get y is equal to plus or minus the square root of x. So you kind of see the square root function here, but it's a positive square root and it's also the negative square root function. So this I can't graph on my calculator, but you can see every y value here is going from a positive y to a negative y. So I'm just grabbing those points and flipping them. So if it really does have x-axis symmetry, I'm going to reflect about the x-axis, and this point 3, 2 is going to go down here to, all I'm doing is replacing that y with a negative y. So this goes to 3, negative 2. This will flip down here because that's reflected about the x-axis. To flip about, or to reflect about the y-axis, I'm replacing what? X with negative x. So the red becomes the blue. So in this case, if I just have a point, again, 3, 2, definition of y-axis is to replace the x with a negative x. So this point becomes negative 3, 2. And you can see that's reflecting about the y-axis. I'm replacing x's with x's. If it flips or reflects about the origin, I'm going to change both signs. The x's and the y's go to negative x's and negative y's. So this point 3, 2 would actually go to negative 3, negative 2. Again, that's said to be an odd function or reflects about the origin. So those are the three scenarios, and here are the definitions. Symmetry about the origin, I'm replacing everything, both x's and y's. To test, if I don't give you a graph, to test for symmetry, I'm going to test first of all for x-axis symmetry. Remember, I'm going to replace the y with a negative y. So instead of saying y is equal to, I'll say, here comes my first test for x-axis symmetry. I'll replace y with a negative y. So the question is, does negative y equal the same function? Do I get the exact same function back? And if I do, then I say that it has symmetry about the x-axis. But if I multiply both sides by negative 1 here, I can see y was equal to the opposite of the function. If that's not the same, that's exactly the opposite. So I'm going to say no, this does not have symmetry because I didn't get this to look exactly like this. It was the exact opposite. Let's test for y-axis symmetry. And y-axis symmetry says replace every x with negative x. So instead of y is equal to x squared, I'll say negative x squared minus y over negative x squared plus 2, which, notice, this simplifies to the exact same function. And that means that it does have symmetry. Because if I replace every x with a negative x and I get the same value, then I know it has symmetry. You can also test for about the origin. But again, I don't think this will work because you're going to get the opposite function again. This scenario is going to happen. I'm replacing y with negative y and x with negative x. But again, I think I get the same thing as I did up here in blue. It's the opposite. And so I would say no, that does not have symmetry about the origin. If I were to graph it on my graphing calculator, you can see that it surely does have symmetry about the y-axis. But on your